monitoring the chat, and we'll go from there.
Sure. Hello, everyone. Yeah, oh, sorry. Is that all right? Okay. Okay. Hello, everyone. I'm Chirag Bhansali, and I'm a freshman majoring in computer science. So today I'm going to talk about quantum error correction and decoding techniques. So the aim of this talk is to give you a brief overview of what quantum error correction is, how it works, where decoders and decoding techniques come in, how they all work from a broad point of view. I'm going to give you an overview of it. So first of all, let's talk about how error correction works in classical computers. So the most general type of error is the bit flip. So the 0 bit can be flipped to 1 if an error occurs. So how we circumvent it, we use redundant coding to detect and correct errors. So the simplest version is to just keep on adding multiple copies of each bit. So if there's 0, we can create it like 3 bits of 0 and 1 to 3 bits of 1. So if any of the bit it gets corrupted due to an error, we can use the majority rule code to find what was the original set of information. However, this cannot be done in qubits because you cannot clone, or you cannot add redundancy with qubits because cloning, you cannot create exact copies because of the no cloning theorem. So the workaround with quantum error correction is to spread the information of 1 qubit onto a highly entangled state of several qubits. So by doing so, if any of the 1 qubit is lost or becomes corrupted, the encoded information can still be recovered from the remaining qubits. So what this basically was a quantum error correcting code. So error correcting code, it's used in quantum computing and communication to protect quantum information from errors caused by noise. So as you saw in this equation, we encode the information into a larger number of qubits to allow it to be recovered, even if some number of the qubits are corrupted or lost due to noise or other errors.
I want to ask a question.
Sure. Sure.
You said the most common kind of error for classical computers. What other kinds of errors do classical computers deal with?
I'm not really sure about what like the other kind of classical error correction codes are. Yeah, errors. So, yeah.
I could opt
Sure.
one. Reset, just always flip to 0.
That's so. Oh, I see what you're saying. So
Always flip, so it's
so
not
0 never is affected, but 1.
right.
I see.
Right.
Okay.
Okay, thanks. So the main group of quantum error correcting codes are known as stabilizer codes, and they have many types. So there are repetition codes, surface codes, topological codes, and polar codes. In today's talk, I'm going to focus on surface codes. So what happens in surface codes is you encode quantum information into a 2D lattice of qubits with stabilizer generators that act on sets of 4 qubits arranged in a square. So what are stabilizer generators? They're like set of Pauli operators that commute with each other and they're used to define a stabilizer code. And these generators, they're then chosen to form a stabilizer group that commutes with all the operators, and that represents the encoded quantum state. I'm going to show a diagram which will help make things clear in the next slides. So this is sort of what it looks like. I'll come back to this in a moment. So to detect and correct errors in the qubits, surface codes use a set of measurements known as syndrome measurements. So syndrome, it sort of represents the error that happened in the qubit. So these measurements are made by measuring the parity of the stabilizer generators, which basically means measuring whether the product of the eigenvalues of the generator is +1 or -1. And these measurements then provide information about the presence of errors in the qubits. So this is an example of a surface code of a qubit. So as you can, so these edges, they represent qubits. And then there are like two kind of stabilizers comprise 2 types of local operators. So as you can see, this one, this is a Z operator, and they're like they connect 4 qubits like this. And then around the plackets, these are the X operators. So any questions so far about surface codes? Yep.
So you mentioned stabilizers here, but on the previous slide, you called them something else. So there's 2 different things, or
No, what do you mean?
so So here you call this measurement syndrome measurement.
Yeah.
On the other slide, you say they're stabilized. You measure the stabilizer.
So syndrome measurements is what, so stabilizer, it's like stabilizer codes are a group. Under them, then come the surface codes. This is an example of a surface code. Stabilizer codes are, it's like an overview, it's like a broader category. This is what, under stabilizer codes comes surface codes. It's a type of stabilizer code. And syndrome measurements are, they're made by like measuring the parity of, like you measure whether the product the eigenvalues of the generator is -1 or +1. Any other questions so far?
So since those are the stabilizers, that means you've restricted your choice for the states of the qubits on the edges, right?
Yep.
So each of the flat, the P and the V, they have to.
Yeah.
The states have the eigenstates of those with eigenvalue.
Yeah.
Right.
Yep.
For all, okay.
Maybe I'm getting ahead of you here, but how do you deal with boundary conditions here?
Sorry?
How do you deal with boundary conditions here? So like in the top right corner.
Yeah.
Right, if you try to place this V stabilizer there, it's only gonna have 2 qubits to work with instead of 4. So do you use some sort of periodic conditions or?
I think it does extend this like sort of just part of the image. It does extend beyond that. I don't think it ends there.
Well, it can't go on forever, right? We have a finite number of qubits. What would happen at the boundary, regardless of how far out it is?
I think it just does the corner two then. It doesn't. Yeah. So I'll move to decoding. So a decoder, it's an algorithm. So what it takes as input is a check operator, which is the syndrome, and it attempts to find a correction operator, which helps in correcting the error that may have occurred. So a check operator is just a matrix that acts on a quantum state to detect the error that occurred in the system. So here I'm going to give an example of how all of this works. So as you can see, we have a stabilizer operators. There's a quantum computer in which an error might occur. And then there's this syndrome that we find out. Then we use a decoder to find a recovery operator, which will correct the error. So I'll give some examples. It will become more clear. So as you can see here, we have this syndrome, which there's a -1 and +1. And the stabilizer or the operators that we are using are Z1, Z2, and Z. So if you look at this, so look at the first operator, Z1, Z2, it's anti-commuting. So that's why there's a -1. And it's commuting with the other operator, Z2, Z3. So which is how we can deduce its X1. So X1 will anti-commute with Z1, Z2, but it will commute with Z2, Z3. So the recovery operator will basically, so the error is basically X1, and the decoder finds the recovery operator to correct that error. So there's one more example. And so would anyone like to try out like what might be the error in this case? We have this syndrome, and based on the syndrome and the operators, what could be an error?
We're detecting bit flips, is that right? Like,
Yeah. So I'll move on. So basically, as you can see, since it's anti-commuting with both of them, with both of the operators, it must be the X2 operator, since Z2 is in both of these operators. So the decoder then finds a recovery operator based on the error, which was the X2 operator. Yeah.
So your computational basis is no longer the normal spin down for each qubit basis, right? You're now working on the basis of the eigenstates of those data.
Yeah.
That's.
So I'll move to decoding techniques. So how basically, what kind of, sorry. Yeah.
So are there any unrecoverable errors?
Okay.
Errors that you cannot recover from?
Sorry, what is your question? Can you repeat that?
Are there any unrecoverable errors? It looks like all 4 possible -1, -1.
Yeah.
Seem to be okay.
Yeah. In this example, I think there are no unrecoverable errors.
There is. Anything that can be switch stabilizers. Yeah.
Okay.
Should be unrecoverable
Okay.
errors. Basically just all phase errors.
so if in this case, if you had a lot of bit flips. So if you got all of them flip.
Yep.
You would flip to another valid state. Okay. So you wouldn't be able to detect it. You would just, you'd be like, you're good, you know, this, it's good, we should exist, right? So, yeah, these, in this case, you have to assume, the probability of a lot of flips occurring is pretty small. But more likely for it to occur.
So I'll move on to decoding techniques. So there are several of them. In today's talk, I'm going to focus on minimum weight perfect matching, but I'll give a brief overview of the other ones. So there's something called maximum likelihood decoding. So as the name suggests, you calculate the probability of each possible error syndrome, given the measurement set of errors and the encoding circuit used. And in renormalization group encoding, it starts by dividing the qubits into smaller groups, and then you use a decoder to correct the errors in those particular small groups. And then you merge all those results to decode the entire system. So if you would have heard of divide and conquer, it sort of sounds similar to that, not exactly the same thing, but it's like you divide them into smaller groups, decode them, and then combine on the system. So I'm going to focus on, in the next few slides, on minimum weight perfect matching. It's going to be a bit text heavy as I'll explain certain terms, and then there's going to be some images that will make it clear what I'm talking about. So it's this method, it's used to decode the syndrome measurement results and determine the most likely error syndrome that caused the errors. So it works by constructing a graph where each node represents a possible error configuration, and each edge represents the compatibility between two error configurations. So by configuration, I just mean like possible errors that could have occurred. And the weight of each edge is the number of qubits that differ between two possible error configurations. So how it works is you find the perfect matching with the lowest total weight in a graph, and that corresponds to the most likely error syndrome. The matching provides the information needed to correct the errors in the qubits. And I'm going to explain what matching is, what a perfect matching is, what's the minimum weight in this. So as you can see here, matching, it's like a set of non-adjacent edges in a graph. So let's just take this as an example. So a set of non-adjacent edges might be these horizontal ones or these vertical ones here. So, and a perfect match is a matching which touches all the nodes. So since this only has 4 nodes, the set of horizontal edges will be a perfect matching. Now, a minimum weight perfect matching is the perfect matching which minimizes the sum of the edge weights. So here I'm arbitrarily assigning weights to each of these edges. So let's say the ones on the left and right have 1 and 2, and the ones on up and like the top and bottom have 3 and 4. So the minimum weight perfect matching would be the vertical ones in this example. Any questions with the terms that I've used here? Matching, perfect matching, I think.
How do you assign those weights?
Right now, I'm just assigning it. It's an example. In a real error, it's defined like based on the errors. So as you can see, like we formulate this as a graph problem, and then we represent a syndrome S as a graph. And we use an algorithm called Blossom algorithm to solve this minimum weight perfect matching that we find out. So as you can see, it's like in the edges, they represent the qubits. The ones marked in red, they have errors. And the blue stars, they represent the defects in those edges. If you see some of these, since they're like adjacent to each other, there's no defect in the middle one because they are canceled out by each other. Now, what you do is basically you arrange all the defects as nodes and draw an edge from each node to every other node, which makes it a syndrome graph. And what the aim is basically to find a recovery operator R, so that we can find a perfect matching of V. And to do that, we use an algorithm such as the Blossom algorithm. So I'm not going to explain how that algorithm works, but what we get from it is it's a perfect minimum weight perfect matching. And once we place it on a graph, we find a correction operator from it, which can be used to like get the original encoded information. Any questions on this so far?
So there's like 2 different graphs going on. There's this geometry of the surface code, and then you construct a different graph, which is like connecting all the nodes, which are the defects, right? And then you find a perfect matching for that graph. Is that right?
Yep.
Okay.
Yeah, you map them.
And will a perfect matching always exist for that graph? Or
I think it does.
minimum
Yeah,
weight perfect match?
I think it does. Yeah.
This is all about not only one people on the classical computer, it's interface with this.
Yep. It's a classic algorithm. This is like, it's, yeah.
You know the complexity of the loss algorithm, if I had 80 qubits.
I'm not sure about that. Yeah, but
But
it's,
it's efficient. So,
yeah, it's inefficient. It's like one of the most popular techniques, like convert. That's, yeah. So to conclude, so this is like, I'll just like briefly explain again how it's working. So first we measure the syndrome using a set of stabilizer generators and determine the presence of errors. And then we identify the errors by mapping the syndrome onto a graph of the surface code. Then we use an algorithm like the Blossom algorithm to find the perfect matching that minimizes the sum of the weights of the edges. And then since we get a error correction operator, which we can use to find the originally encoded information. Any questions about MWPM so far?
I don't know if you're gonna get to this, but I don't think I see how the this matching helps you correct the errors. Have you already touched on that, or are you gonna get to that?
No, I'm not. No, it's not like there actually for this. Yeah,
Okay.
yeah.
I thought it was that this finds the correction operator, you can just apply that, or the deeper, right? You just apply that to your basis, right? And that would take you back.
Oh, so the matching, because those nodes connect to Pali operations, so
So,
you,
so once you map this onto a graph, this is your correction operator.
oh, okay,
Yeah.
okay.
And when you apply when you apply this, you get the original information.
And to be clear, this does not necessarily match up with the red. So,
No, no.
you know, the errors. So this is, it's funny because they look similar, but
Yeah.
they're different.
Yeah.
They'll end up being different.
Yeah, because it was like just to explain, but it's not necessary that it will match. It was just an example in the starting. Yeah, they're not related to each other. Yeah.
Gotcha.
Yeah.
Okay.
And one like what are the like challenges that are there in quantum error correction? So I mean, adding redundancy to qubits it's a very powerful technique to mitigate errors, but there are some limitations associated. So one of them is like, as you add more qubits, it limits the practical stability of quantum systems because it becomes more computationally expensive to decode them, and there's like it limits the speed and efficiency of the quantum systems. So brief like summary, what happening, you first encode quantum states into highly entangled states consisting of more qubits, and after that errors can still occur. Some of the encoded states they become corrupted, so that's why we use decoders to detect the error and then apply the required recovery operator to retrieve the original quantum state. So that's basically what's happening in quantum mechanics. Yeah. Any questions so far?
Yeah, actually,
Is that
Sure.
so far as
No, I think that's the end of the talk.
Oh,
Yeah,
okay.
yeah.
I did want to go back to the weight.
Sure.
Is this guaranteed to give you, let me motivate my question. When you apply this correction operator, you're applying it on the bottom of it means it can induce its own errors, it may not be applied correctly, and therefore bonus. So
Yep.
we kind of want this correction operator to be as simple and small as possible.
Yeah, exactly.
Is this, in this picture, it's a large product and sum of poly operators on different disparate units. Is this kind of guaranteed to give you the smallest string of poly operators? Because you get the word minimally, which makes me think it might actually also do this. But do you know if it does?
I don't think it guarantees it. I mean, that it's not like this is the perfect method to find it, but it's one of the most like efficient, accurate methods to doing it. I don't think we still, I mean, it's quantum error correction is still an ongoing problem. It's not fully cracked, so it doesn't guarantee anything right now.
This is still only for bit with no phase error.
Yep.
So you mentioned the other two types of finding the error. Why would we want to use those rather than the minimum weight for matching?
You mean these ones?
Yeah, why would we want to use either of the other two?
Actually, I don't know much about these other two right now, but I'm sorry.
We have lots of time, folks, so if we have more questions, we can be like overhead of this.
Sorry,
Or
yeah,
actually.
Okay.
This is generic, right? So I can choose the overhead.
Yeah.
But by which I mean the number of extra qubits I need to protect. and
Yeah.
qubits.
Yeah.
That will depend on your code. Yeah. Yeah. Absolutely. So I think I think I'm still missing the connection between this this process. So we've constructed this graph and applying the correction operators according to this matching corrects the errors. I guess I just don't see why. Like, why does that work? You know, I think you've explained what to do very, very well. I think I understand it, but
yeah.
maybe what I'm missing the reason why it works. Do you have an idea or an explanation for that?
I'm not very sure, like how to explain that. Yeah.
Chirag, if you go to the picture of the surface code. Yeah, this one. Can people in the room hear me, by the way?
Yeah, Ryan, we can hear you.
Okay. So it's as Chirag explained, it's sort of in this picture, it's by virtue of how you represent the problem. Here, the representation is that edges are errors and the blue stars are the defects, or the syndromes that you measured as -1. So in this picture, anytime an error happens, we have a red edge, and that flips the two adjacent stabilizers. So you get blue stars there. So here we're imagining we know what the error is. And so we're starting with the red edges, and then we're taking that and figuring out what the blue stars, what the syndrome would be. But now we don't know what the error is, so we have the reverse problem. So on I think the next slide, Chirag, all you're given is the blue stars, and you need to find some set of edges that's compatible with this. And that's exactly the perfect matching problem that Chirag nicely explained. It's just this problem in graph theory that fits onto this problem now that we've represented it this way. So any perfect matching is a valid error that could have produced this syndrome that we have. And then we assume that we want the minimum weight perfect matching, which is to say that we would favor edges that are close to two nodes rather than far away. We take the distance to be the length of the Pauli error string that would have occurred. So that's essentially an assumption about locality. Does that help explain? I think, was it Jacob who asked this question?
Yeah, thanks, Ryan. What really helped was reminding me that we have no idea what the actual layout of errors looks like. So you're just sort of trying to find a plausible, it's like you're trying to find a plausible layout that would have caused that syndrome graph. Is that sort of right?
That's right. This graph here. Yeah. And so any perfect matching could produce this, and then you want to find the minimum weight one. And then once you do that, that corresponds exactly to the recovery operator.
I think that goes back to the minimum weight part, is that we assume that the least number of errors to get from a state to this state is what happened, not the most number of errors. Right. Even though we're in the disk era, that doesn't really matter.
Well, other questions or, yeah, so, okay, so I'm gonna rephrase my asymptotic complexity question. If I have n qubits and I want to be able to detect, say, one or correct one bit flip and detect two, how many extra qubits do I need?
I'm not sure about that.
I think you have to, in this surface code, I
Yeah.
think you can't ask for a different amount of detections than corrections. So then you can either detect as many as you can correct, or you can't correct them all.
I don't, I'm pretty sure that you can use I know this is the case classically, and it's probably also the case quantum mechanically, that a simple pigeonhole argument shows that you can detect more things than you can correct. Sometimes the students are not for classical error correcting codes.
What was the question? What is the minimum number of qubits you need to correct one error?
Yeah, for n, if I have n message qubits, or n qubits, n logical qubits, whatever you want to call them, how many qubits do I need to correct, say, or correct one bit flip?
If you have n qubits,
Extra overhead, or is it proportional to n?
I don't understand. So you're saying you have n qubits and then you want to know how many additional qubits you need?
I think. Yeah, so I might be phrasing this in the terms that are used in classical error correction, but you have message, you have so many message bits that you care about. And those are the things you want to protect. Then you have extra error correcting bits.
Ah, okay, I see. Yeah, I think it's the same terminology. I don't know if ancilla is used in classical error correction, but I think you're asking about this. I don't remember there are bounds like this that are known. I don't remember them. I think you have to to correct an arbitrary single qubit error, you need like 5 physical qubits. And so that consists of,
Or does that increase if you have more qubits protected?
sorry, can you say that again?
Is that a constant 5 extra qubits, 5 extra physical qubits, or does that increase with the number of logical qubits? For message?
Oh, it increases in general, yeah.
Yeah, I think the source of the confusion is usually when we talk about logical qubits as being some number of physical qubits, so they are correctly proportional. So it's 5 physical qubits. I think what Ryan's saying is just 5 physical qubits. For this error, now you scale up your system. Okay, it's all on top of the top. Okay, yeah, high speed. Yeah, and message qubits, and then kind of add 4. Yeah, so I mean, Ryan and Chirag have both done more error correction than me, but I usually do this for things in terms of I suppose it's not in still certain number of physical qubits, right?
Yeah, I mean, if Chirag, you go to the slide which has the syndrome, or sorry, the surface code picture. For example, here, each plaquette and each vertex, so the P and the V, you need an ancilla qubit to measure these operators. And so you can imagine the number of ancilla grows with the size of the lattice.
Right, that's what I thought. All right, thank you.
Going back to the correction versus. Has it been corrected here in the sorry, no, it does not detect anything different from what it corrects. It will give you a correction for any qubits that have had an error. It won't tell you that it's
Right, the correction isn't guaranteed to be correct.
absolutely, that's what I'm saying. It doesn't tell you that,
But
hey,
it's not correcting error, that's actually.
but it doesn't tell you that it's detecting the error that it can't correct. There's no way for that to happen. It will always give you back a correction. It doesn't.
I don't think you understand what I'm saying. I'm saying that it's guaranteed to correct, the response is guaranteed to be correct for some number if the error is less than or equal to some number.
Yes.
And you are guaranteed to detect And some other number of, you're guaranteed to be able to detect if some other number of errors has happened. I think, can I ask that we, table this discussion, maybe both of you can talk afterwards. I'm not sure if the rest of the room is eager to follow along with this. Okay, are there other questions? Any comments? Well, maybe in that case, then that conversation can happen. Sooner than expected. Let's thank you all one more time.
Yeah. Thank you.
Yeah, I think maybe Chirag, if he's willing.